In the winter of 1961, a scientist typed a single number into a computer, went to get a cup of coffee, and, without knowing it, shattered one of the oldest dreams in science. The dream that if we just measured carefully enough and calculated hard enough, we could predict the future. He proved, by accident, that we can't, and the reason why is one of the most beautiful ideas of the 20th century. His name was Edward Lorenz, and he wasn't trying to overturn anything. He was a mild-mannered meteorologist at MIT, a mathematician by training who'd fallen in love with weather during the Second World War. He just wanted to do something useful and modest, predict the weather a little better. This was the dawn of computer weather forecasting. Lorenz had built a tiny toy model of the atmosphere on a primitive machine, a Royal McBee, slower than a modern digital watch, that filled a room and clattered like a typewriter. 12 numbers, a dozen equations standing in for the whole sky. One day, Lorenz wanted to re-examine a particular weather sequence his machine had produced. Rather than start the long run from the very beginning, he took a shortcut. He read a set of numbers from an earlier printout, typed them back in as a starting point, and set the machine running again to repeat the sequence. Then he walked away to let it run. When he came back an hour later and looked at the new results, he was baffled. The weather his machine had just produced was completely, wildly different from the run before, not slightly off, utterly unrecognizable, a totally different sequence of storms and calms. At first he assumed a vacuum tube had blown, or the machine had glitched, but when he traced it back, the truth was stranger and far more important. The machine was working perfectly. The only difference between the two runs was the number he'd typed in. Here's what had happened. Inside its memory, the computer stored each number to 6 decimal places, say .506107. But to save paper, the printout Lorenz had typed from was rounded to just 3.506. So when he re-entered the starting point, he was off by about 1 part in 10,000. A tiny, seemingly meaningless difference. 1 part in 10,000. Smaller than any error you could ever measure in the real atmosphere. Lorenz naturally expected it to make, at most, a tiny difference in the forecast. That's how everyone assumed the world worked. Small causes make small effects. Nudge the input a hair, and the output shifts a hair. But that's not what the machine showed. That microscopic difference in the starting number didn't stay small. It grew, and grew. The two weather runs tracked each other closely at first, nearly identical for a while, and then began to drift apart, faster and faster, until they had absolutely nothing in common. Lorenz sat with this and slowly grasped what it meant, and the implication was staggering. If a difference far too small to ever measure could completely change the forecast, then long-range weather prediction wasn't just hard, it was impossible. Not because our instruments are bad, because of the fundamental nature of the atmosphere itself. Think about how radical that was. For 3 centuries, since Isaac Newton, science had run on a comforting promise. The universe is a clockwork machine. Know the present precisely, apply the laws of physics, and the future unrolls, predictable and certain. This was the bedrock faith of science. One famous mathematician, Pierre-Simon Laplace, had put it grandly, an intelligence that knew the position of every particle in the universe could calculate the entire future and the entire past with perfect certainty. Nothing would be uncertain. The future was already written. We just couldn't read it yet. Lorenz's clattering little weather machine had just quietly demolished that dream. Because even in a system that was perfectly deterministic, his equations had no randomness in them at all. The future was fully determined by the present. The future was still, in practice, unknowable. The clockwork was real, but you could never read the clock precisely enough to predict it. This is the paradox at the heart of the whole story, and it's worth saying slowly because it's genuinely mind-bending. The system is completely deterministic. The exact same starting numbers always give the exact same future, and yet it is completely unpredictable because you can never know the starting numbers exactly, and the tiniest gap explodes. Determined, yet unpredictable. Those two words were supposed to be opposites. Lorenz had found a world where they were the same thing, and he realized this wasn't a quirk of his toy weather model, it was a property of a huge class of systems in nature, anything with the right kind of feedback loops. He gave the crucial property a name that has since become famous, sensitive dependence on initial conditions. It's a mouthful, so let's unpack it. Initial conditions just means the starting state, where everything is right now. Sensitive dependence means the outcome depends so sensitively on that starting state that any imperfection, however tiny, eventually takes over. To publish this, Lorenz needed to strip his weather model down to its absolute essence, something simple enough to study and understand. So he boiled the atmosphere down to a bare-bones model of one thing, a fluid being heated from below, like air over a warm road or water in a pot. Convection. He reduced it to just 3 numbers, changing over time, governed by 3 simple equations. 3 variables. That's all. You could write them on an index card. And yet, when Lorenz let those three equations run, they produced behavior so intricate and unpredictable that mathematicians are still studying it today. In 1963, he published it all in a paper with a title that gave no hint of the revolution inside: Deterministic Non-Periodic Flow. It appeared in a meteorology journal, and for years, almost no one outside weather science noticed. One of the most important papers of the century, hiding in plain sight. To feel why Lorenz's discovery is so unsettling, let's watch that sensitive dependence in action. Imagine we run his three equations twice. The first time, we start from some exact set of numbers. The second time, we start from numbers that are almost identical, different by a tiny fraction, far less than you could ever measure in reality. At first, the two runs are indistinguishable. They rise and fall in perfect lockstep. You'd swear they were the same. For a while, prediction works beautifully. A small error stays small. This is the reassuring common sense part. But watch what happens as time goes on. Slowly, the two lines begin to peel apart. The gap between them, which started microscopic, doubles, then doubles again, then again. The error grows exponentially, and once it's large, the two runs go completely their own ways, as different as two totally unrelated weather patterns. That exponential doubling is the mathematical engine of the whole thing. A 1 in 10,000 error, doubling every so often, becomes a 1 in 1,000 error, then 1 in 100, then it swamps everything. The tiny seed of uncertainty grows until it fills the entire forecast. That's why the future runs out. And here's the killer. It doesn't matter how good your measurements are. Suppose you measure the atmosphere 1,000 times more precisely. All that buys you is a little more time before the error explodes, maybe a few extra hours of forecast. To double your prediction window, you'd need to measure exponentially better. It's a losing race you could never win. This is why your weather app is confident about tomorrow, decent about 3 days out, shaky at a week, and basically useless beyond about 2 weeks. That roughly 2-week wall isn't a failure of technology. It's a fundamental limit, baked into the physics of the atmosphere. Better satellites and faster computers can nudge us toward it, but never past it. Sit with how strange that is. We can predict a solar eclipse to the second 1,000 years from now. But we cannot tell you if it'll rain in your town a month from Tuesday, and we never will be able to. Not because rain is more complicated than orbits, but because rain is chaotic, and orbits mostly are not. Now, a crucial clarification, because this idea gets badly mangled. Chaos is not the same as randomness. A random system, like a rolled die, has no rule. The same setup can give different outcomes. Lorenz's system is the opposite. It's rigidly ruled, with no randomness at all. The same exact start always gives the same exact future every single time. So chaos is not disorder, and it's not randomness. It's something subtler and stranger, perfectly lawful behavior that is nonetheless unpredictable, because we can never specify the starting point with infinite precision. It's unpredictable in practice, but perfectly reproducible in principle. That distinction is the whole subtlety of the field. And Lorenz, thinking about how to explain this to non-scientists, reached for a vivid image. In an early version, he imagined a single flap of a seagull's wings, somewhere far away, eventually altering the course of the weather. Later, a colleague sharpened it into the phrase that would make the whole idea famous. In 1972, Lorenz was scheduled to give a talk, and the organizer, a scientist named Philip Merriles, needed a title. Lorenz hadn't supplied one, so Merriles invented it himself. And it was perfect. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? The name stuck gloriously. The butterfly effect. It's now one of the most famous phrases in all of science and, ironically, one of the most misunderstood. So let's get it right, because the popular version is wrong in an important way. The butterfly effect does not mean that a specific butterfly causes a specific tornado, in some traceable chain you could follow. You can't blame a hurricane on one insect. What it really means is this: the atmosphere is so sensitive that influences as small as a butterfly's flap are enough to make long-term prediction impossible, because you could never track them all. It's not a statement about causation. It's a statement about the limits of knowledge. The butterfly isn't the cause of the storm. It's a symbol of the countless, immeasurably small influences that guarantee the future will always outrun our ability to compute it. Now, none of this would have grabbed the world's imagination if it were just an abstract argument. What made chaos unforgettable, what turned it from a meteorology footnote into a scientific revolution, was that Lorenz's three little equations, when you actually drew a picture of them, produced something of impossible, haunting beauty. Here's the idea. Lorenz's system has three numbers changing over time. So at any instant, you can plot a single point in three-dimensional space using those three numbers as coordinates. As the system evolves, that point moves, tracing out a path, a curve that draws the entire history of the system. Now, you might expect one of two boring outcomes. Either the path settles down to a single resting point, the system reaches equilibrium and stops, or it falls into a repeating loop, cycling around forever like a clock. For centuries, those were the only two long-term behaviors anyone thought were possible. Lorenz's system did neither. When you let it run and trace the path, it does something no one had ever really seen. It winds around and around, spiraling outward on one side, then suddenly jumps across and spirals around on the other side, then jumps back, looping endlessly, never settling, never repeating, and yet never flying off to infinity either. And when you let it run long enough and look at the shape the whole path fills out, you get this. One of the most iconic images in modern science, two great looping wings joined in the middle. It looks unmistakably like a butterfly, which is a coincidence so perfect it feels designed. This shape is called a strange attractor. Attractor because the system is drawn toward it. Whatever starting point you pick, the path quickly ends up wandering on these wings. Strange because of what that wandering is like, and this is the deep, gorgeous secret at the center of chaos. Look at the attractor and you see order, a definite, elegant, stable shape. The system always lives on these two wings. It never does anything wildly outside them. That's the predictable part. But now, follow a single path along the wings and you find pure unpredictability. You can never say in advance which wing it'll be on next, or when it'll jump. That's the profound thing chaos revealed. Within the apparent randomness there is hidden structure. The behavior looks erratic moment to moment, but it's confined to a beautiful, precise geometric form. Order and unpredictability woven into the same object. Chaos isn't the absence of order, it's a deeper, stranger kind of order. And the attractor has another almost unbelievable property. Zoom into any part of it and you find more structure. The wings are made of infinitely many layers, sheets within sheets, never quite touching. Zoom in further and there's more detail at every scale, forever. The attractor is a fractal, a shape with infinite fine structure. In fact, its dimension isn't a normal whole number. It's not a two-dimensional sheet or a three-dimensional solid. It's something in between, about 2.006 dimensions. A shape with a fractional dimension. This was a whole new kind of geometric object, and it was lurking inside three simple equations about heated fluid. Two great truths live in this single image. The path never exactly repeats. Trace it for 1 billion years, and it never draws the same curve twice. And two paths that start a hair apart will end up on opposite wings, doing completely different things. Never repeating and infinitely sensitive. The butterfly's wings, in more ways than one. This picture, the strange attractor, is what turned chaos from a curiosity into a science. Because once people knew what to look for, they started seeing these strange attractors everywhere. Chaos, it turned out, was not some rare exception. It was one of nature's favorite tricks. Tripping faucets, beating hearts, electrical circuits, chemical reactions, the swirl of cream in your coffee. Populations of animals booming and crashing. Once scientists had the mathematics of chaos, they found its fingerprints across all of nature, anywhere the right kind of feedback loops existed. And that's the real reason Lorenz's accidental discovery mattered so much. It wasn't just about weather. He had stumbled onto a universal feature of the world, a reason that vast swaths of nature are fundamentally, permanently unpredictable, no matter how much we learn. To see just how universal, let's look at one more example. One so simple, it seems impossible that it could be chaotic. It's a single line of arithmetic, a toy model of a population of animals. And it contains, hidden inside it, the entire road from calm to chaos. The idea is this. Take a population, say, fish in a pond. Each year, they breed, so the number grows. But if there are too many, they run out of food and starve, so the number falls. Growth times crowding. One simple rule, applied over and over, year after year. What could be simpler? Now turn one dial, the growth rate, how fast they breed. Turn it low, and the population settles to a steady, boring number, the same every year. Turn it up a bit, and something odd happens. The population stops settling on one value and starts alternating between two, high year, high low, forever. Turn the dial higher, and it splits again. Now cycling through 4 different values before repeating. Higher still, 8. Then 16. The pattern keeps doubling, faster and faster, the splits coming closer and closer together. This is called period doubling, and it's a road leading somewhere remarkable. And then, at a certain growth rate, the doublings pile up infinitely fast and the population goes chaotic. It jumps around with no pattern at all, never repeating, wildly sensitive to where it started. From one dead simple equation about breeding fish, pure chaos. The same unpredictability Lorenz found in the weather. And here's the part that stunned mathematicians. The exact way this happens, the precise rhythm of those doublings, turned out to be a universal constant, the same for a huge range of totally unrelated systems. Chaos doesn't just appear everywhere, it appears the same way everywhere. There are deep, hidden laws inside the disorder. So, chaos is real, it's everywhere, and it puts a hard wall on prediction. That sounds like defeat. But here's the beautiful twist. Understanding chaos didn't make us helpless. It made us smarter about how we deal with an unpredictable world. It changed the very meaning of forecasting. Take weather again. If a single forecast is doomed to diverge from reality, what do? The modern answer is elegant. Instead of running the forecast once, you run it many times. 50, 100 times, each starting from a slightly different guess at today's conditions within your measurement uncertainty. Then you watch what those many runs do. If they all mostly agree, if the whole spread of futures looks similar, you can forecast with confidence. If they scatter wildly, you know the atmosphere is in a sensitive, unpredictable mood, and you forecast with humility. You stop predicting the future and start predicting the odds. This is called ensemble forecasting, and it's why your weather app now says 70% chance of rain instead of a flat yes or no. That percentage is chaos theory in action, an honest measure of how predictable the atmosphere is right now. We turned the butterfly effect from a defeat into a tool. And weather's just the start. Once scientists understood chaos, they found it, and learned to work with it. Across an astonishing range of fields. The human heart, for one. A healthy heartbeat has subtle chaotic variability, and certain deadly arrhythmias are chaos gone wrong. Insights that shape how we understand and treat them. Ecologists found chaos in animal populations, explaining why some species boom and crash in ways that look random but follow chaotic rules. Engineers found it in circuits and structures. Chemists found it in reactions that pulse and swirl. Even the stock market shows chaotic behavior. One reason it so stubbornly resists prediction. And then there's the most humbling example of all, the one that brings us full circle to the clockwork universe that chaos overthrew, because it turns out the solar system itself, the very image of predictable order, is chaotic. For short times, thousands, even millions of years, the planets march like clockwork, and we predict eclipses and alignments with breathtaking precision. But over tens of millions of years, tiny gravitational nudges between the planets amplify, chaotically. We genuinely cannot predict the exact positions of the planets 100 million years from now. Now, an important reassurance, because this fact gets misreported. Chaotic does not mean unstable. The planets aren't about to fly out of their orbits or crash into each other. The solar system is expected to stay broadly stable for billions of years. What's lost is only our ability to know the precise details far in advance. Stable but unpredictable in the fine print. Even Newton's perfect clockwork, it turns out, has chaos woven into it. The universe is deterministic, the equations are exact, and yet, over the long run, its detailed future is unknowable. Laplace's all-knowing intelligence, calculating everything from the present, is not just practically impossible. It's impossible in principle, in a universe like ours. It's worth pausing on how strange it is that we didn't see this coming for 300 years. And, in truth, one person nearly did, decades before Lorenz. At the end of the 1800s, the great French mathematician Henri Poincaré was studying the motion of three bodies pulling on each other by gravity. Poincaré discovered that this three-body problem could behave with staggering, tangled complexity, that tiny changes in the starting conditions could lead to wildly different orbits. He had glimpsed sensitive dependence, the seed of chaos, in the 1890s. But he had no computer to bring it to life, and the insight faded into a difficult corner of mathematics. It took the computer, a machine that could crank the equations forward thousands of times and show you the results, to make chaos undeniable. Lorenz's clattering weather machine did what Poincaré's pencil never could. It let the butterfly effect play out in front of human eyes. Chaos needed the computer to be born. And still, for years, Lorenz's discovery stayed buried in the meteorology literature, largely unknown to the wider scientific world. Chaos was a secret hiding in a weather journal. Then, in the 1970s and 80s, a scattered band of mathematicians, physicists, and biologists, often working against the skepticism of their peers, began independently rediscovering and connecting these ideas. Chaos slowly assembled itself into a whole new field, cutting across every science. It was a genuine scientific revolution. And in 1987, a writer named James Gleick published a book simply called Chaos that told the whole story: Lorenz, the attractor, the butterfly, the universal constants for a general audience. It became a huge bestseller, and it planted the phrase, the butterfly effect, permanently into the culture. Suddenly, chaos was everywhere. In movies, novels, conversations, the butterfly effect became a household phrase. Usually mangled, often reduced to a vague, everything is connected, but rooted in a real and profound scientific truth about the limits of prediction. A piece of deep mathematics had become part of how everyone thinks. Through all of it, Edward Lorenz remained exactly what he'd always been: quiet, modest, a little bemused by the fuss. He kept doing careful science, kept hiking and cross-country skiing well into old age, and rarely made a big deal of having upended 3 centuries of scientific certainty by mistyping a number. There was no Nobel Prize in mathematics or in meteorology, so the field's highest honors couldn't formally come his way. But science found other ways to recognize him. In 1991, he received the Kyoto Prize, one of the world's most prestigious awards for having, in the citation's words, brought about one of the most dramatic changes in humanity's view of nature since Newton. Think about that. A mild meteorologist tinkering with a toy weather model is placed alongside Isaac Newton for changing how we understand the universe. And he did it not by adding certainty to the world, but by revealing, forever, the limits of certainty itself. Because that's the real gift of chaos theory. It's not a gloomy story about what we can't do. It's a truer, humbler, richer picture of the world than the clockwork one it replaced. A world that is lawful but surprising, determined but open, knowable in its rules, unknowable in its details. A world where a system can obey perfect, rigid laws and still be free to astonish you. Where simple rules give rise to endless, non-repeating complexity. Where the same mathematics that limits our weather forecasts also paints those impossible, beautiful butterfly wings. It all came from one rounding error on one winter morning on one clattering machine, noticed by one person curious enough to ask why, instead of just shrugging and blaming the computer. Which is, when you think about it, a very good lesson about how discovery actually works. Let's come back to that machine, and that moment, because it holds a lesson worth carrying with you. Lorenz's discovery didn't come from a grand experiment or a huge budget. It came from an anomaly, a weird result that didn't make sense, and from a scientist who refused to look away from it. He could so easily have just shrugged. The computer glitched, I'll rerun it. Almost anyone would have. Instead, he asked the small, stubborn question, why are these 2 runs so different? And followed it all the way down to a truth that reshaped science. Great discoveries often hide inside the results we're tempted to ignore. And the deepest lesson of chaos itself is a kind of intellectual humility, one that our prediction-obsessed world badly needs. We love to believe that with enough data, enough computing power, enough cleverness, we can forecast anything: markets, elections, pandemics, the future. Chaos says, for many of the things you care about most, you fundamentally can't. And that's not a failure. It's the nature of reality. This doesn't mean prediction is worthless. Far from it. It means we should be honest about its limits, humble about the long term, and smart about working in probabilities instead of false certainties. Chaos doesn't tell us to give up forecasting. It tells us to forecast wisely and to hold our long-range confidence loosely. There's something freeing in it, too. If the universe were the perfect clockwork Laplace imagined, then everything, every choice, every event, the whole future, would already be fixed and, in principle, readable. Chaos restores a kind of openness. The future is not a book already written that we simply can't yet read. In any world with chaos, the fine details of the future are genuinely open until they happen. And chaos gives us one more gift: it dissolves a false divide. We used to think there were 2 kinds of things: simple, predictable systems and complicated, random ones. Chaos revealed a vast, fascinating middle ground: simple systems that generate boundless complexity and hidden order living inside apparent randomness. That middle ground is where most of the interesting universe actually lives. The weather, ecosystems, the economy, the rhythms of the body, turbulent water and swirling galaxies. Not clockwork, not random, but chaotic, lawful and surprising at once. Lorenz didn't just find a quirk of weather, he found the texture of reality. So the next time you see a weather forecast hedge its bets, or hear someone say, the butterfly effect, you'll know the real story. It began with a tired meteorologist, a rounding error, and a shape like a butterfly's wings, and it ended with a whole new understanding of what the future is and isn't. You'll know that the butterfly effect isn't about a butterfly causing a storm. It's about the profound truth that in a universe like ours, the smallest unknowable things shape the largest outcomes, and that this makes the long-term future not just hard to predict, but impossible to predict, no matter how godlike our knowledge becomes. And you'll know that this isn't a gap in our knowledge waiting to be filled. It's a permanent feature of the world, as fundamental as gravity, as real as the speed of light. Unpredictability built into the fabric of a lawful universe. That's one of the strangest and most beautiful things science has ever discovered. It took the whole 20th century and a wacky accident to learn a lesson the universe had been quietly keeping all along, that being determined and being predictable are not the same thing. That perfect laws can still hold perfect surprises. That even in a world run entirely by mathematics, the future gets to remain open. Edward Lorenz gave us a more honest universe, less certain, but more alive. A universe that will keep surprising us no matter how much we learn, not because we're not smart enough, but because that's simply how reality is built. And there is something wonderful about living in a world like that. Because a fully predictable universe would, in a way, be a finished one. Every future already fixed, nothing genuinely new left to happen. Chaos means the universe is never finished. It's always creating, always unfolding details that were never determined in advance in any way we could read. The butterfly's wings keep the future forever open. There's a poetry to how it was found, too. A pattern that looks like a butterfly, discovered by accident, describing why a butterfly's flap matters, while teaching us that the deepest truths are often hiding in the results we're most tempted to throw away. The whole story rhymes with its own lesson. So hold on to the real butterfly effect. Not the pop culture version about everything being connected in some mystical way, but the precise, hard-won scientific truth that in a chaotic world, tiny causes can have enormous consequences, that the long-term future is fundamentally unknowable, and that this is a feature of reality, not a flaw in our tools. And maybe hold on to the smaller lesson too, the human one, that a revolution in our understanding of the universe came from one person paying close attention to something that didn't make sense. From curiosity about an anomaly, from asking, why, when it would have been so much easier to shrug. That's a kind of butterfly effect all its own. One small act of curiosity, on one ordinary morning, rippling outward across decades and disciplines until it changed how all humanity understands the future. Small causes. Enormous consequences. It works for ideas, too. We began with a promise that was 3 centuries old, that the universe is a clock we could learn to read perfectly. And we end somewhere richer and truer, a universe that runs on perfect laws and still keeps its surprises, a future that is written in mathematics and yet remains, in its details, gloriously open. The clock is real. We just learned we can never read it precisely enough to spoil the ending. And honestly, a universe like that, lawful but forever capable of astonishing us, sounds like a much more wonderful place to live than a clock whose every tick was already known. From a rounding error to the edge of predictability itself, that's the story of the butterfly effect, a reminder that the universe is deeper than our certainties and that its greatest secrets sometimes hide in the numbers we almost threw away. Stay curious about the results that don't make sense, the glitches, the anomalies, the runs that come out wrong. Every so often, one of them isn't a mistake at all. It's the universe, trying to tell you something it's never told anyone before. If this story stuck with you, do 2 quick things. Hit subscribe. Neat Science brings another forgotten story back to life, and there's a whole playlist of them waiting for you right now. And tell me in the comments, which part of this surprised you the most? I read every single one. So keep exploring. Your next story is just 1 click away. I'll see you there.